All right, so I want to give you another little lecture here on an example of non-relativistic effective field theory applied to cold atoms. So we'll talk about constructing a cold atom EFT. So this is a nice example where usually we're taking examples from particle physics, but the ideas of effective field theory are actually much broader. They apply to condensed matter physics, and they apply to atomic physics. And we'll see that with the example that we do here today. So we're going to follow the rules of constructing an effective field theory. And the first thing we have to think about are what are the scales in the problem. So if we're talking about atoms, well, there's, of course, the mass of the atom, m atom. And this is typically in the GeV range. I'll express all the scales in energy units. There's the Bohr radius of the atom. So A0 Bohr, inverse to express it in energy units, and this is keV. There's the typical binding energy, say, of hydrogen. So then this is some electron energy, and this is like 10 eV. But we're talking about very cold atoms, so we're actually talking about energy scales that are much smaller than these. So let's keep going. There's another correction that comes in, which is called the hyperfine splitting between atoms. This is a spin-spin interaction, and it comes in at the 10 to the minus 3 level. So we have 10 to the minus 3 electron volts. But if we keep going, there's even further energy scales in the problem. There's a vibrational energy scale that comes in at 10 to the minus 6. And actually, what we're interested in for cold atoms is the actual energy for the cold atoms, and that's at 10 to the minus 10. So we're really talking about very, very low energy atoms here. And all these scales above are integrated out. So if you like, these are our lambda, and we're keeping just this very low energy scale E cold. What kind of systems does this apply to? Well, you might be interested in studying Bose-Einstein condensates at 10 to the minus 10 electron volts, very cold system. You might be interested in studying other atoms like helium or lithium or sodium. So they don't have to be bosons, they could be fermions, and what we'll talk about here will apply equally well to bosons and fermions. Another example is helium atoms. So there's lots of different examples that are studied. And we're going to be pretty generic in our construction here, so what we'll do will actually apply to all these different cases. So one thing I want to point out with this construction of scales here is if we're integrating out the hyperfine interaction, that actually means that the spin splitting, usually we'd say spin is a good symmetry, like the Coulomb interaction preserves spin. So we have two spin states and they're degenerate. But if we integrate out the hyperfine interaction, then that's no longer true. The lower energy state is the ground state. The other one is integrated out. So it's very, very far away. So spin is broken as a symmetry, which I can denote like this. So that's one thing. And another comment here is about this vibrational scale. This applies even when you have neutral atoms. And the type of interactions that are responsible for that are the van der Waals force. So this is the van der Waals force, giving rise to that one. OK, so this is a non-relativistic system. And the type of dispersion relation that we have for a non-relativistic system is simply, for kinetic energy, is E is p squared over 2m. OK, so we want to construct an effective field theory that has that property, that as its dispersion relation. The other thing that we want to think about, of course, are symmetries. And the symmetries will depend exactly which system here that we're talking about. So let me come to that in a second. I should make a note for the degrees of freedom. So we're talking about some field, psi of x, that annihilates an atom. And I'll just use this generic notation. It looks like a fermion, but it could equally well be a boson. And then we'll have, of course, psi dagger to do the creation of the atom. And then we have to sort of enumerate all the symmetries that we think are good symmetries. And that's going to help us to think about how we construct the system. And so one thing that we have, just like in HQET that we talked about, there's no pair creation, because the pair creation is something that's very far away. It costs basically twice an atom. So we don't have that. So we have a U1 for particle number. in the system. We have rotational invariance. Even though we don't have Lorentz invariance, we are a non-relativistic system, we still have rotational invariance. So rotations are good. And that means basically if we think about derivatives, they're always going to come in pairs. So we might have some gradient, spatial derivative, and we'd have to dot the gradient into some other gradient in order to satisfy a rotational symmetry. Other good symmetries are things like parity and time reversal. Very often those are good symmetries. Charge conjugation's of course broken because we don't have the antiparticle. But parity and time reversal may still be good symmetries that we can impose on our construction of the Lagrangian. And then finally, there is a remnant of Lorentz symmetry related to the boosts, and that's the Galilean boosts. This one is a little bit special. It's actually only a symmetry at lowest order in the expansion. So what is the expansion? Well, it's an expansion, as usual, in this scale here in the denominator with energies or momenta in the numerator. So let me just say that we're expanding in p over lambda much less than 1. And when we do that expansion, if we work at lowest order, the system will be Galilean invariant. But once we start including corrections, in particular relativistic corrections, it will no longer be Galilean invariant. So in some sense, this is a lowest order symmetry, whereas some of these others may be exact symmetries of all the dynamics. OK, so that's the setup. And now we just have to construct the Lagrangian. So let's do that. We've talked about nucleons in lecture. So some of this is similar to that, and I'll tell you how that works. So first of all, we're interested in the kinetic term. So this is sort of responsible for the propagator. This is an integral d4x with two psi fields. And if we want that dispersion relation, we just have a time derivative, and then grad squared over 2m, and then relativistic corrections, psi. This is what the kinetic term looks like. In lecture, we talked about the power counting for exactly this action, so I'm not going to review that here. I'll just remind you of how it works. So because this is a non-relativistic system, the d4x scales like p to the minus 5. Each of the spatial coordinates scales like a p to the minus 1. And then time scales opposite to energy, so it scales like p to the minus 2. And that's where the p to the minus 5 comes from. If you take the fermions to scale like p to the 3/2, and this in the brackets here is a p squared, and this is also a p squared, those terms are the same order, then when you add everything up here, you have something that adds up to p to the 0. So if you like, what we're doing is we're fixing the normalization for the fermion here such that we get p to the 0, and that's just a convention for how we determine the scaling of our fermion field, or our boson field. Psi could be a fermion or a boson. And that's what the kinetic term basically tells us. And now we start doing interactions, and we can use that scaling to figure out what's going on with the interactions. So, OK, so let's look at the sort of leading order interactions. And the leading order interactions in this system are actually two-body short-range interactions. I'll talk about long-range interactions in a few minutes, but we'll start by just talking about short-range interactions. OK, so what is a two-body short-range interaction? Well, if this guy here has two fermion fields, or two boson fields, we're going to have more. They always come in pairs because of this U1 particle number. So we're going to have 4 fields in this Lagrangian. So let me call it L2 body. It's going to have an integral d4x. And then it's going to have some terms like C0, psi dagger psi, psi dagger psi. Or you could have some terms with derivatives, like psi dagger. And this derivative with an arrow both ways means acting left minus acting right. And it's a notation we've used before. And then we could have 4 derivatives, et cetera. The derivatives always coming in pairs in order for the rotational symmetry to work out. So this is the type of Lagrangian that is a two-body interaction Lagrangian. And this Lagrangian is actually exactly the same Lagrangian that we already talked about for nucleons. So I, again, don't want to go through it in any detail, but I'll just remind you of what the story was there. If you go through the power counting, you have the same p to the minus 5 for this d4x. Now you've got 4 fermion fields, so you're getting p cubed times p cubed, which is p to the 6, so you're getting an overall p. And that means the C0 here in this term here would have a 1 over lambda. And actually, if you're careful about the mass dimensions, you actually learn that the C2m for the mth chi goes like 1 over the mass of the nucleon, or the atoms in this case, and the nucleon in the case where we worked this out in lecture, in our other lecture. And then you get a power of lambda. If you keep doing that for C2, you basically have these 2 extra derivatives. That gives you 2 more lambdas. So the general case is 1 over m to the lambda of the 2n plus 1, and that's the power counting for the C2m's. OK, so that's what the two-body interactions look like. And the story here is actually exactly like what we had for nucleons. So really what I want to do in the rest of this lecture is just sort of talk about some other types of interactions that could show up and convince you actually that these ones are the most important. And then the story about exactly how you do loop diagrams and everything very much follows this discussion that we had for nucleons in the other lectures. OK, so one thing that's different about atoms is that we might have different symmetries than we did in our nucleon case. So let's just think about that for a minute. I said that the psi could be a boson, it could be a fermion. So what is that? What is the difference mattering here? Well, if it, for example, just to sort of do this by way of example, if we just had a single fermion field, and when I mean single fermion, I mean only one spin state. Then you just have, then if you multiply 2 of those together, that's 0 because of the antisymmetry. This has to be antisymmetric, but psi equaling minus psi implies that psi is 0. If you had 2 spin states, you could have 2 fermions that are multiplying with different spins, and then it doesn't have to be 0. So that basically says if you only have a single fermion with one spin state, you're basically going to have something that distinguishes these fields, like a derivative interaction. And otherwise, it'll be 0. So that's an example of how symmetry, in this case just fermions, symmetry would imply things about the operators. Another example is if psi was a boson, then you have to have Bose symmetry, exchange symmetry. So if you have this derivative that has a minus sign when it acts on the 2 fields, something like this would be 0 for psi of boson, because it has to be symmetric in the interchange of the bosons, and this operator is actually antisymmetric in the interchange of the psis. OK, so that's an example of how symmetry could actually constrain things. OK, so that might reduce some of these operators. It might mean there's less of them. In some cases, if there's more internal symmetries, it might mean there's actually more operators. And we actually saw that when we did nucleons, where there was 2 different types of C0s. All right, well, let's talk about other types of interactions. This two-body short-range interactions, things that happen at a kind of interactions like this, where the 2 particles come in, and then they interact, and then they go out again. What else could happen? Well, the natural thing to think about is, well, what about 3 bodies? So we could have 3-body interactions. It's another type, obviously. Let's see if this marker works better. It does. OK, so this is the natural generalization of our 2-body interactions. And it simply means that we have 3 particles. And if it's, again, short range, which is what I'm thinking about, they all 3 would interact at a point. So we can just repeat this story here, but now talk about L3 body. Again, we have an integral d4x. Now we would have an operator that has, say, psi dagger psi cubed, and then higher order terms. And if we go through the power counting here, let's do that. So this guy here is p to the minus 5, as always. And then now we have here p to the 9. OK? So that means that this guy is going to have 1 over lambda to the 4th power. And if we actually work out precisely what it is, it'll also have an m in it. So it's actually 1 over m lambda to the 4th power. So these interactions here are suppressed by p to the 4 over lambda to the 4. OK, so 3-body interactions are down relative to 2-body interactions. OK. All right, so that's a description of the short-range interactions. And we could keep going with that story and talk about 4-body interactions, and they would also be suppressed. Let's come now to long-range forces. Okay, so there can be long-range forces between the atoms, and how do we describe those? I'm going to limit myself here to a particular type of long-range forces, which are the most relevant type and the only type that are actually useful for the cold atoms, which are instantaneous in time. Okay, so this is like a Coulomb interaction that happens at an instant in time, this exchange between the atoms. Of course, a Coulomb interaction would only happen if the atoms are actually charged. So we should think about other long-range forces as well. So let's just set up a general Lagrangian to describe the long-range forces. So because there's our long range, there's actually some separation, spatial separation. And we can think about them being described by a potential that I can write in the following way. So let me take a psi dagger psi that's at a point x, have a potential that's a spatial potential that goes from x to x prime. It's a function of the difference. And then have a psi dagger psi at a point x prime. And these are at the same time but different spatial locations. So the x and the x prime have the same time in them. So this is an interaction that we could draw as follows. And then this potential here is an exchange between those two sets of fermion fields. And then these are the points that we're labeling x and x prime. OK, so this is what we mean by a long-range force. Let's do some power counting. First thing to do. Now we have a different measure here, so we have to be a little more careful. There's a p to the minus 2 here. Each of these gives a p to the minus 3, so that's 6, and that's 8. OK, so that was different than our p to the minus 5 that we had in our previous examples. And then we have our psi dagger psi, psi dagger psi. So this is a p cubed, and this is another p cubed. And the potential, that'll depend on exactly what potential we're talking about. So let's summarize this by saying the L long range goes like p to the minus 2 from the things that we can count. And then depending on the power counting of the potential, which I'll denote by putting a square bracket, sort of the dimensions of the potential, but here the dimensions of the potential in units of the power counting, which is this p. OK, so the L long range will scale like that. And now we can do some simple examples of what kind of long range forces are interesting for atoms. So if there is something that's charged in the system, then, and in some sense the simplest long range force is Coulomb. So let's start there. The Coulomb force is a potential that goes like 1 over r, and it could be attractive or repulsive. And so this goes like p. So the v is scaling like a p. 1 over r scales like p. And that tells us that the L long range in this case is p to the minus 2 times p, which is p to the minus 1. And there's this factor of alpha, which I'll include. And there's also a factor of m. And that just comes from the time, just as it did in the, when we counted m's in the nucleon example. So what we have here is something that we can actually define as alpha over a v, where v is the relative velocity. V is equal to p over m, and that's the relative velocity. And this is the scaling that one has for a Coulombic system, that we have the long-range force goes like alpha over v. It'll be important if v is of order the fine structure constant, alpha, that's governing that interaction. And if it's not, if v is bigger than that, then it might not be. Or if the atoms are neutral, then we just don't have this force at all, because instead of having a plus or minus, we'd have a 0 here. And that's actually typically the case that we study, because we don't want this long-range force to be important. If the Coulomb long-range force is not important, then there's another long-range force that actually is important. That's the van der Waals force. So let's also do that. The van der Waals force is a force that goes like r to the 6, 1 over r to the 6. So let's have some coefficient divided by r to the 6 for our van der Waals force. So this scales like p to the 6. OK, so the p dimensions of the v here are 6. So the L long range gives a, subtracting 2 gives a p to the 4th. And then we have a c6. OK, and then we also have an m, if we count the m, the mass dimension that comes out of the t, getting that mass dimension right. OK, so this is the kind of the scaling for that long-range force. And we can turn this around and say, actually, what it means is that m times c6, since this is dimensionless, m times c6 should scale like a 1 over lambda to the fourth. Okay, we could call this something related to the van der Waals, and then it's raised to the fourth power. So put some subscript on it. It's not too important. All right, so this is the power counting here, but you see again it's suppressed. It's suppressed by p to the fourth over lambda to the fourth. So this long-range force for atoms, for neutral atoms, this applies even for neutral atoms, is a suppressed interaction. And we would just deal with the short-range interactions until we got to order p to the fourth. Once we get to order p to the fourth, then we have to think about the van der Waals. But until we get there, all the interactions in the system are very simple. They're just given by those two-body short-distance interactions, and then at some point the three-body comes in the manner that we just derived. And that's it. That's the theory of cold atoms. You can now think about using this theory to make predictions. You could use this theory, for example, to study Bose-Einstein condensates. If we wanted to do that, we wouldn't be thinking about a system with the type of interactions we're having here, which is two particles in the system, like a scattering. We'd actually be thinking about the situation where we'd have a density. So you'd add a chemical potential, and then you could add a chemical potential to the Lagrangian and study a system at finite density. You could study things like Bose-Einstein condensates, where you get a condensate of atoms, break symmetries, the Goldstone bosons, which are phonons of the system, all sorts of great stuff. And what we've outlined here in this lecture is just the starting point of studying this very interesting effective field theory.